This example involves combining our knowledge of exponential and log functions. As we can see in the equations that we need to match to the graphs, we have two exponential functions, I and II, as well as two log functions, III and IV. So going back to our knowledge of exponential functions and what they look like, B and D are the only ones that match the shape and the characteristics of exponential functions, while A and C match the shape and the characteristics of log functions. We can deal with this however we want now that we've split it up into our two separate sets. If we deal with log functions, we can see that C, as it moves up from left to right, would mean that we have a standard log function and that our A value must be positive. Looking at our equations, III has a positive 6 value for A, so that one would match up with C. And graph A, moving down from left to right, is an inverted log function, meaning that the value of A would have to be negative, so IV matches up with A. Turning to the two exponential functions, we can use the same logic here. Graph B follows a standard trajectory, moves up left to right. The other piece of information we looked at when dealing with exponential functions was the y-intercept. And the y-intercept of this function I know is difficult to see, not only because I've drawn over top of it, but because of the scale of the graph. It is at about 5, which, looking at equation I, the A value of 5 tells us that's where the y-intercept should be, so that's what matches up with this graph. D, that exponential function moves down left to right, which tells you that our base must be less than 1. It is. It's 0.1. As well, the other piece of information pointing us to that equation match is the y-intercept, which is here at 2. And the A value from that function is 2. So graph D matches up with equation II.